Welcome again to the new lecture of this course on solar photovoltaics, principles, technologies and materials. So, what we have covered in last few lectures is, it's going to be recap of last few lectures. So, we talked about second generation solar cells or second generation photovoltaic technologies. Which were based on thin film based devices, and in this category we mainly studied amorphous silicon solar cells, we studied cadmium telluride based solar cells, then copper indium gallium selenide based devices, and then finally we looked at multi junction. These are primarily four technologies that we talked about in the last few lectures. So, now we will move on to the third generation technologies. So, these are called as third generation PV technologies, and these are primarily because there is a potential to overcome Shockley-Kaiser limit, and that limit places efficiencies at about 31 to 41%, and there is a potential in these technologies to overcome this limit. The technologies of concern are to begin with a close cousin of CIGS, which is copper zinc tin sulfide. We commonly call it as CZTS. Then we have dye sensitized solar cells. Then we have organic solar cells, and of late in last few years we have perovskite solar cells, and there is another technology which is quite interesting, is quantum dot solar cells. And of course, in these we can also add tandem, because these devices are also coming in tandem solar cells. So, tandem includes 2G and 3G, it was also present in 2G and it is also present in 3G technologies. So, if time permits, so primarily we will look at dye sensitized solar cells, organic solar cells and perovskite, because these are three distinct technology from the 2G technologies. Copper zinc tin sulfide is fairly similar technology to CIGS solar cells. So, we will not cover this in this lecture. However, if you are interested to read about it, there are plenty of web articles and journal articles in which you can read about this technology. It is a potentially interesting technology with efficiencies of the order of so CZTS has an efficiency of about 10%. So, this has efficiency of about 10%. Dye sensitized solar cells give you efficiencies of the order of about 12%, so roughly 12%. Organic solar cells, if you look at in tandem form, then more than 15%, and so this is for tandem, and single junction will give you about 12 to 14% devices. Perovskite solar cells have exceeded 21%. The world record now stands at about 23%. Quantum dot solar cells are at about more than 10%, and tandem cells in these perovskites have crossed 20%, whereas in organics they have crossed 15%. So, we will look at the middle three technologies, that is these three technologies in detail in the next couple of lectures. We do not have time to go through quantum dot and copper zinc tin sulfide, but if time permits I will cover them in a lecture or so. So, let us look at first the organic solar cell technology. We will begin with organic solar cell. Now, this is an interesting technology because here we do not use inorganic materials, rather we use organic compounds which are called as either small molecules. So, these are organic small molecules or polymers. So, basically their composition consists of carbon, hydrogen, nitrogen, sulfur, etc. is present in these materials, and these materials became prominent after discovery of so these becomes popular after discovery of electrically conductive polymers. So, you can say electrically, not thermally, but electrically, okay. And this resulted in a Nobel Prize to Heger, McDermid and Shirakawa in 2000. This is chemistry Nobel Prize. This discovery, although it was made a lot earlier, it opens a floodgates for a different kind of electronics away from silicon electronics, and this gave rise to these organic materials, polymeric materials which could conduct electricity. They were semiconducting materials. So, these are semiconducting materials which can be made by simpler processing in the lab, and that is their USP. To make oxide, you need to dig out things, make them react. To make telluride, you need to have cadmium source, tellurium sourse, and generally the processing of those materials is high temperature processing. Silicon is made through high temperature processing, cadmium telluride is made through high temperature processing, indium gallium selenide is made through high temperature processing. These can be made in the laboratory through simpler processing at lower temperatures. Also, these are organic materials, they are flexible. So, you can make devices which are on plastic substrates, they can be lightweight and so on and so forth. One of their close cousins is already in application, that is in displays. So, displays are already commercialized. So, you have these OLED displays in mobiles, AMOLED displays in mobiles and TVs and all that. Samsung and LG, they are competing with each other. They are already commercialized. In this, in the present courses context, we are going to learn about their use in organics in solar cells. So, these are materials which can be made potentially through low cost, although right now the cost is very high because the processing scale up has not been done, but there is a potential to lower the cost in terms of processing. They are flexible, they could be lightweight, they are also, many of them also biodegradable, and you can tune them, you can tune their composition very easily, they can be processed at lower temperature. So, these are certain advantages of using organic solar cells. So, if you look at the conductivity variation in materials, and this is electrical conductivity, by the way, not thermal conductivity. So, and this is in Siemens per centimeter. Okay. So, metals have a conductivity which is of the order of 10 to the power 0 to 10 to the power 4 Siemens per centimeter, whereas semiconductors have in the range of 10 to the power minus 2, I don't know, to 10 to the power minus 8, whereas for insulators it would be less than 10 to the power minus 8. Okay. And generally your silicon and germanium will fall in the range of 10 to the power minus 4 or so. Silicon and germanium will fall around minus 3 to minus 4 or maybe minus 5 depending upon the composition. So, if you look at quartz on the other hand, SiO2, this has a conductivity minus 18 Siemens per centimeter. If you look at copper, it has a value of 10 to the power 6 Siemens per centimeter. So, you want polymeric materials to have conductivities which are in the order of semiconducting range. This was not possible earlier. Most of the polymers were insulating, so they were, you can see in electrical sockets and various other applications, most of the plastics that we use are insulating. However, the discovery of this by Alan Heger and Shirakawa and McDermid, that opens the floodgate for designing compositions in organic materials which could be conducting. And this happens mainly because suppose you have an organic molecule, okay, and this has okay. So we have these atomic orbitals. They, let us say, two molecules are making a bond. So of course it has these. And so on and so forth. So, between these pi lobes, between these p lobes on z side, so there is a sigma bond here. So, let us say this is a, I do not know, maybe you can take ethylene molecule, all right, or you can say, you don't know, you can take pentacene molecule. So, in these things along the carbon chain you have a sigma bond which is a strong bond. But on the periphery we have pi bond and this double, so you have this double bond here between the sp2 hybridized carbons. So, these carbons are sp2 hybridized, but on the periphery we have this, between the pi lobes we have pi bonds, and these pi bonds are weaker in nature, and along these pi along the outer periphery there is a conduction that takes place for electrons. If you provide the composition, if you have composition which is appropriate to make this happen, and this generally happens by doping. So, for example, if you do sulfur doping in polymers, for example in benzene, right. This gives rise to what we call as thiophenes. This allows this pi-pi transport along the pi channel. So, it is not present in every polymer, it is present only when you dope it appropriately, and this doping comes from the external elements, other elements, second elements like sulfur. So, generally in many organic materials the archetype or the you can say the basis is benzene molecule, and when you start putting benzene molecules together, then we start forming these compounds. So, basically what we want to do is that we want to, the idea is to delocalize the pi electron. See, pi electrons are present in other molecules as well, but they are not delocalized, they are localized. And when the electrons are localized, they are not able to travel. So, you have to make them delocalized just like you have in metals to make them travel and to experience less force on them. So, when you delocalize the pi electron upon doping, these materials become conducting. So, these delocalized electrons are necessary for conduction to occur. So, and this does not happen along the sigma bond, it happens along the pi bonds, because pi bonds are weaker as compared to sigma bonds. So, it is easier to delocalize the electron in the pi bands than in the sigma bands. So basically this happens upon doping, and this is where you have materials like polythiophene, we have pentacene, which are conducting. So if you look at polythiophene structure is something like this. So you can see that your benzene ring otherwise is like this, and it does not allow conduction because the electron is not localized. So by introducing these sulfur ions here in these rings, you have made it delocalized. So this is what you do in polythiophene, you also do it in pentacene and various other materials, and polythiophene has been a workhorse material in organic solar cells. So when you dope these materials with elements like sulfur, the molecules with extended sp2 hybridization states become what we call as pi conjugated materials. So these materials are also called as pi sp2 hybridization state. So sp2 hybridization state is not localized, it is extended over a whole chain. So as a result, these presence of these sulfur atoms here, it allows the conduction of electron to occur along the chain through the pi band. So if you look at conductivity comparison, so polythiophene, for example, polythiophene has a so the dopant in this case is SO3 CF3-, this is dopant, and if you look at sigma values in Siemens per centimeter, it gives you a value of 10 to 20. Okay, it's quite strongly conducting. If you look at for example polypyrrole, FeCl3 is the dopant, and you get conductivity variation between 3 to 200. So they become strongly conducting as against their undoped counterparts, which are strongly insulating. So this is the power of doping in polymers, which basically creates delocalized pi electrons which can conduct along the chain of the molecule, giving rise to conduction. So these materials make the backbone of electronic, you can say organic electronic devices, and solar cell is one of them. So materials which are based on these are called as organic solar cells. There are two kinds of materials which we generally use. One is called as small molecules. Small molecules are the materials which are materials of a small molecular weight. They do not have extended chains, smaller molecular weights, and then we have polymers. Polymers are of higher molecular weight. Generally, polymeric solar cells are preferred because small molecules are difficult to be synthesized through solution processing route. They can be synthesized nowadays, they can be synthesized through solution processing route, but small molecules are generally used in devices because they have very good evaporation capabilities. You can evaporate them just like metals. but evaporation is a process which does not allow you to make large area devices. So, making large area large area devices is not very easy using small molecules. That is why most of the organic solar cell research has concentrated on the use of polymer, because polymers can be easily solution processed. So, material like polythiophene, so it is called as poly 3 hexyl thiophene, which is called as P3HT. Okay. This is a polymer, but material like, you can have a pentacene. Pentacene is it's not a polymer, it is a small molecule, it can be evaporated easily. So, we generally focus on polymers instead of small molecules in organic solar cell research, although there is no discredit to small molecules community. There are a lot of good solar cells which have been made using small molecules, using both evaporation and solution deposition, but we will mainly consider on polymer solar cells in this lecture. So, we know that in a solar cell what happens is that we have light comes onto the solar cell, then you absorb the light. So, in a normal solar cell, so first step is you have light incident, then light absorption. After light absorption, you have exciton formation and dissociation into free electron and holes. After this, we have separation of charge. So, you have transport of charges, and after transport you have collection at the in the normal inorganic p-n junction solar cell. These steps are relatively straightforward. The light comes, light is absorbed, you form exciton. Exciton has very low binding energy and it readily dissociates into free electron and free hole. The free electron and free hole are swept away on either side of the junction through inbuilt electric field, and this built-in electric field and these carriers transport to the junctions to the electrodes, and then they are collected. However, in an organic device, while the steps remain the same, in case of organic, this exciton dissociation is a problem. Is rather complex, because exciton binding energy of exciton, and then again exciton transport, then carrier transport is also an issue, because carriers have a smaller these excitons also have a smaller diffusion length. So, exciton must dissociate into carriers before the carriers are recombined. So, carriers must find the electrode before they recombine and form the exciton again. So, these two steps, exciton formation, dissociation and transport, these steps are really critical in case of organic solar cells, and this is what has been the focus of behind the design of present architecture of organic solar cells. So, in case of organic solar cells, exciton formation, exciton diffusion and exciton dissociation, these are the things which are of utmost importance. So, exciton formation, exciton diffusion and exciton dissociation, these things are extremely important, and of course, you would like to minimize the recombination as well to back into excitons. So, we will just mention the energies in excitons here. So, exciton binding energy in case of inorganic solar cell the exciton binding energy is of the order of kT. So, they get dissociated very easily using the thermal energy. In case of organic materials, this energy is about 0.2 to 0.3 electron volt, much higher than kT. So, it is higher than kT, it could be as high as 0.2, 0.3 or even 0.4 electron volt. This energy has to be supplied from somewhere. So, that is why you need to create a junction in such a manner, so that you have enough electric field available to break this exciton, and this has to come from the constituents of the solar cell. So, that is why the choice of P and N type material is critical, so that one has enough built-in field to break the exciton into electron hole pair, and then this exciton also has short diffusion length. The diffusion length of exciton is of the order of few tenths of nanometer. So, exciton has to be broken away before this diffusion length. So, this creates a concern on the device design, which means your device thickness is also of the order of few tenths of nanometer if you have a single layer or bilayer devices. So, based on these two constraints, so there are three designs of solar cells which are possible here. When it comes to organic materials absorption coefficient, organic semiconductor absorption coefficient, they act as a direct band gap semiconductor, and they have high absorption, but the band gap of these materials is generally higher than 1.5 eV. Okay, so their band gap is on the higher side, but they have good absorption coefficients. So, if you summarize these materials, they are direct band gap semiconductors. They have relatively higher band gap, they have low exciton diffusion length, before electron and holes recombine. This is the maximum length they can travel. So, you can say about, it could be anywhere between 10 to 60 nanometer, and then they have high exciton binding energy. Keeping these constraints in mind, you need to design a binding energy of the order of 0.2 to 0.3 eV. Keeping these constraints in mind, you need to design a organic solar cell. So, the first layer design of organic solar cell is single layer device. So, what happens here is basically you have a single polymeric material like this. In case of polymers, another thing that you will come across is, instead of calling them conduction band and valence band, we call the band edges as LUMO and HOMO, where LUMO is equivalent to conduction band edge in inorganic materials. It is not similar, but it is equivalent, and this is basically called as lowest unoccupied molecular orbital. See, the thing is, these are not ordered materials. That is why the band theory isn't really applicable to these materials, because they are aperiodic materials. So, we talk here in terms of molecular orbitals instead of energy bands, but there are certain similarities which one can make, and then the lower one is called as HOMO, which is similar to valence band edge in inorganic materials, and this is called as highest occupied molecular orbital. So, in these materials, when the light comes in there, the electron get excited from here to here, it goes here, electron, and forms a hole. However, until it is separated, it remains an exciton. So, now this exciton will separate towards one of the electrodes. So, you have these electrodes on this side, and this, so they will diffuse to this side together, and then the work function difference between the two metals on two sides will provide them enough energy so that they can dissociate, so that your hole will come to. So, first the exciton, first what you will have is exciton forms, second step is exciton diffuses, third step is exciton diffuses towards electrode, one of the electrodes, okay, and that depends upon the exciton where the excitons are created more, whether on top or whether on the bottom. So, and then, so diffusion gradient is going to move the exciton, and then exciton dissociates, and dissociation happens at the interface. So, interface must have some sort of energy to break this exciton. So, these are the three processes, and as we said that exciton diffusion length is about few tens of nanometers. The whole device thickness cannot be larger than few tens of nanometer. If your device thickness is controlled by this diffusion length, which means your solar cell cannot be very thick. If your solar cell is not very thick, so this is electrode, you can say this is electrode, metal electrode, this is also electrode, okay. So, you have to use two different metals so that you provide there is a work function difference. So, one is high work function, one is low work function metal. This creates a problem because now if your device thickness is lower, you are not going to be able to absorb a lot of light. So, low thickness means low absorption. So, that is why even though you might absorb the light, you might break the exciton, you simply do not absorb enough number of photons. As a result, your efficiency is low, and this led researchers to make other architectures in the organic solar cells, which we will see in the next lecture. So, we stop here. What we have seen today is in this lecture is about the organic solar cells, the introduction, what is the genesis behind them, what is the motivation behind them. We talked about excitons, why exciton is a problem in case of organic solar cell, and how one needs to evolve strategies to overcome this problem. All right. So, we stop here. Thank you very much.